right, so continuing on with our sample problems for Chem 111. Today we're talking about molecular masses in AMUs, calculations of molecular masses, as well as conversion or masses of atomic components, as well as percent composition. So let's start off. Sodium chromate is used to protect iron from corrosion and rusting. Determine its molecular mass. So the first thing we have to do is figure out what sodium chromate is. Right? So the chromate ion was one of the ones we need to memorize, which is the CrO4 ion. And it has a 2- charge. Right? Sodium is Na. This is a group of non-metal, or metal and non-metal. So this is a polyatomic ion. This is a metal, so this is going to be an ionic compound. So when sodium forms an ion, it forms a +1. So we need then 2 sodiums, the +1 ions, to equal that 2-. So we end up with a molecular formula of Na2CrO4. Right? So we need to calculate its molecular mass, excuse me. So to do that, we have to look at the periodic table. So we're going to take the masses for each one of these elements off the periodic table times the number of them that are present. That'll be our molecular mass. So if we look here, we have sodium, we have chromium, and we have oxygen. From our balanced formula, we have 2 sodiums, 1 chromium, and 4 oxygen. So we're going to take those numbers, multiply by its atomic mass, again from the periodic table, it being 22.99 for sodium, 52.00 for chromium, and 16.00 for oxygen. Right, put those down here, 22.99 AMUs, 52.00 AMUs, and 16.00 AMUs. Right, take 2 times 22.99, we end up with 45.98 AMUs. 1 times 52 is 52. And 4 times 16 is 64 AMUs. Right? So this is the contribution for each element. Add those together, we end up with 161.98 AMUs. Right? We're doing addition here, so we would typically follow that with the fewest number of decimal places. Here, this is multiplication, so I would typically include the same number of decimal places, maybe one more when we do this step. Right? So the atomic or the molecular mass for sodium chromate is 161.98 AMUs. Okay. Let's look at another one. Determine the molecular mass of iron 3 bromide hexahydrate, a substance used as a catalyst in some organic reactions. Again, we have to look at what this molecule actually is. Iron 3, this is a transition metal, so the 3 tells us the charge on that iron. So we have an iron 3+. Bromide, the ending "ide", tells us this is just the element, so which has a Br-. We'll get to this hexahydrate in a second. Combine these two, if we have a 3+ bound with Br-, it takes 3 minuses to equal the 3+, so this becomes FeBr3. Now let's come back to this hydrate form. Right? Hydrate is one of those things we have to memorize. Means there's water included in this reaction, and the hexa tells us how many there are. Right? Hexa is the code for 6, so this would be then 6 H2Os. Right, so this is the molecule that we're looking at, not only the iron bromide, iron 3 bromide, but also the associated waters. So when we calculate its molecular mass, we have to calculate it for everything, including the waters. Right? So again, in this formula, we're going to have iron, we're going to have bromine, we're going to have hydrogen, and we're going to have oxygen. Right? So all the elements represented here have to be down here. Right? The numbers that are associated with iron only has, there's one iron here, there's only one of that part of the molecule, so that is going to be a 1. Bromine, there's a 3 here, so there's 3 of those. Now if we look at the hydrogens, in the water itself there are 2, but there are 6 waters, so that gives us a total of 12 hydrogens within this molecule. Again, 1 oxygen per water, 6 waters, so we have 6 oxygens to include. Again, from the periodic table, we're going to look iron 55.85, bromine 79.70, 79.90. Hydrogen 1.008, and then oxygen again 16.00. Copy those back down. 55.85, 79.90, 1.008, and 16.00 AMUs. Multiply this number by the number of atoms present by their mass, gives us 55.85 AMUs of iron, 239.7 AMUs of bromine, 12.096 AMUs of hydrogen, and 96.00 AMUs of oxygen. Add all those together, we end up with 403.646 AMUs. So the molecular mass of iron 3 bromide hexahydrate, or FeBr3.6H2O, is 403.646. So let's break now these down a little further. Instead of talking about mass, let's talk about subatomic particles. So how many protons are there in a molecule of adrenaline, which is C6H8O3, a neurotransmitter and a hormone? So for this one, we have to then figure out for each atom present, and then the number of corresponding protons for each type of atom. Right? So in this case, the 3 types of atoms that we have here are carbon, hydrogen, and oxygen. Right? We have 9 atoms of carbon present, 8 atoms of hydrogen, and 3 atoms of oxygen. Each carbon atom, again from the periodic table, has an atomic number of 6. Remember, the atomic number is the number of protons there are. So we would multiply this then by 6 protons per atom. Hydrogen, atomic number of 1. So this has 1 proton per atom. Oxygen, atomic number of 8. So this is 8 protons per atom. So multiply 6 times 9, we end up with 54 protons contributed from the carbon. 8 times 1 is 8 protons contributed by the hydrogen, and 3 times 8 is 24 protons contributed by the oxygen, for a total of 86 protons in one molecule, per one molecule. So again, we're just breaking apart this into its individual components and accounting for those. Let's look at another problem. Household sugar, or sucrose, has a molecular formula of C12H22O11. What is the percent of carbon in sucrose by mass? So for this one, remember that the percent by mass is equal to the mass of whatever we're talking about, in this case carbon, divided by the total, or the molecular mass. And then to make it a percent, we have to multiply that by 100. So we have to not only figure out the total mass of carbon that's present, but also the molecular mass. So we're then going to again break this down. Carbon, hydrogen, oxygen. There are 12 carbons present, 22 oxygens, and 22 hydrogens, 11 oxygens. Back to the periodic table to get the mass. Carbon has 12.01, oxygen 16.00, and hydrogen 1.008. AMUs, 1.008 AMUs, and oxygen 16.00 AMUs. Right. So if we look at this, the mass of the carbon, 12 times 12.01 is 144.12 AMUs. Hydrogen, 22 times 1.008 is 22.176 AMUs. And oxygen, 16 times 11 is 176.00 AMUs. So if we add them all up, the molecular mass is 342.28 AMUs. But we're not looking for this number, we're looking for the percent by mass. So we have to take the mass of carbon divided by that molecular mass. So the percent by mass of carbon is equal to the mass of carbon total. Well, there's 12 carbons times 12.01 is 144.12 AMUs, divided by the molecular mass, 342.28 AMUs. To make it a percent, we times it by 100. Do that, we end up with 42.1%. Let's do another one of those. Let's do the percent composition of potassium dichromate. So we're going to look at each element and do the percent composition of each one of those. So, atoms that are present: potassium, chromium, and oxygen. There's 2 potassiums, 2 chromiums, 7 oxygens. From the periodic table, potassium has a mass of 39.10, chromium 52.00, and oxygen 16.00. So then the mass of potassium is 78.20 AMUs. Chromium is 104 AMUs. Oxygen is 112 AMUs. So since percent by composition, or percent by mass, is equal to the mass of the atom divided by the molecular mass times 100. We're going to do that for each one of these. So we're going to calculate the percent of potassium, which is equal to the mass of potassium present, 78.20 AMUs, divided by the molecular mass. And if we add all of these up, we get 294.20 AMUs. Times that by 100, we get 26.58%. And we're going to repeat that process for the other two species present. So percent chromium is going to be 104 AMUs divided by 294.2 AMUs times 100. And the percent of oxygen is going to be the 112 AMUs divided by the 294.2 times 100. So for this first one up here, we're going to end up with the chromium, 104 divided by 294.2, we get 35.35%. 112 divided by 294.2, we're going to get 38.07%. So then if we know the percentages, we can then go back to figure out the number and the masses of each one of those. We can figure out the number of atoms in there, or vice versa.